All right, so let's keep going, and today we're going to discuss primarily distributions, continuous and discrete. So let's start with discrete probability distributions. All right. Okay. Well, earlier we discussed the concept, the notion of random variable. So that's something that varies from one observation to another observation, right? The different people, for example, have different heights, different blood pressure, different pulse rate, different weight, amount of salary, number of education years, etc., etc. So variables can be discrete or random. So in this part, we're going to talk about discrete. Discrete is something that takes only certain values. It cannot be just anything. It takes the value only at the certain, well, numbers, if we're talking about numerical. For example, if you're in a casino and you're rolling a die, one single fair die, your options for the outcome are 1 through 6, right? You cannot get a 2.5, right? It just doesn't happen that way. So the die lands on one of its sides, okay? Another example is how many customers will come into the store every hour. Not a single retailer knows how many customers will visit in the next 30 minutes, in the next hour, today, for example. So Harris Teeter, which is across the street from CNU, right? They can go ahead and track how many customers walk through the door every hour. So from 9 to 10, from 10 to 11, etc. And these numbers will fluctuate through the day because of different reasons, right? For example, probably they can expect a lot of people in the morning before they get to work, right? Grabbing some breakfast or, buying Lunchables or something like that. Then they probably have quiet time, right? Sometime between, let's say, 9 to 12. Relatively few customers come in, and then they have a lunch rush, and then again quiet time, and then in the evening they have a lot of people coming in. So there are some variabilities due to the, well, let's call it seasonality, right, during the day, that are explainable, attributable to certain reasons. But even if you take the same hour, say for example from 9 to 10 in the morning every day, right? From day to day it's going to be a different number, right? So one day they have 111 customers coming in. Next day during the same exact time period they have all of a sudden 223 customers. And then the day after that you have only 75, okay? So things fluctuate because people make random decisions, right? Whether or not to go to the store. It also depends on the weather, probably, right? So there are a lot of factors that affect that decision. But still, the number of customers that come through the door cannot be fractional, right? So it can be 0 if nobody comes in. That's bad, but it's possible, right? It can be 1 customer, 2 customers, etc. 500 customers. And theoretically, there is no upper limit, right? I mean, it's not likely that they will see during 1 hour like 50,000 people, right? 1/3 of the population of Newport News. It's very unlikely, but it still has very, very small probability. So we shouldn't basically exclude that chance, right, from the consideration. So that basically means that the distribution, how many customers, we don't know. This is the variable, right? Number of customers that are coming through the door to the store. That's the variable. It changes, right? From hour to hour, from day to day, it varies, okay? But we can assign, we can basically list all the possibilities, starting from 0 and going theoretically to plus infinity. And to every number, we can assign a probability of that exact number happening, right? And that's basically what we mean by the probability distribution. Essentially, it's a list of possible values, a table, right? It lists all the possible values that the variable can take and their corresponding probabilities, okay? Now, continuous random variable, not discrete, means that it can take any real value. So there are no limitations. Customers, we have limitations, right? It cannot be fractional. Something else, for example, how accurately you can measure time. We can measure time with killing accuracy, right? We can measure time down to the last, decimal. So if you ever watch the Olympic Games, like especially running, right, or swimming competition, it's all about how quickly you run, like 100-yard dash or something like that, right? And oftentimes it's very close call, right? So people basically that compete, they can finish in a very close time. So to make a determination who won the race, they have to measure time down to like fifth decimal, right, or something like that. So time can be measured with very high accuracy. So essentially, it's a continuous variable, right? Same actually applies to the money, right? Money, I mean, when we're living, like these days, money are electronic, right? Like I practically never carry, like oftentimes I carry $0 with me, so I'm broke, essentially, right? Everybody who is married, yeah, same.
When you're married,
yeah, when you're married and you start having kids, that's yeah, that's pretty much it. But from those times when we carried the bills and coins with us, right? The smallest amount of money that you could pay is 1 cent, right? So when I drive past the gas station and I see these prices that say basically $2, 15 cents, and then 9/10, right? It's like, what is 9/10? How can I? Should I take 1 cent and kind of chip away a little bit and give it to them? That's 9/10? No, of course not, right? We can't pay 9/10 of a cent, 0.9 of a cent using the physical money, coins, right? But transaction that we run is electronic, right? And electronically, because all of our money pretty much are in the bank account, and what you have essentially is an electronic record in the database, right? That's your possessions, right? Money are getting away from physical, so we can think of money as outdated instrument, right? Physical money, bills and coins, right? So probably some years down the road, we will not have any physical money at all. So it's all going to be electronic transfers, right? Chip. Or chip, yeah, built into your body, right? Like in those movies, right? So we still have checks. Actually, checks is the probably 19th century technology, right? So they're still around. We can't get rid of them, but this is hugely outdated way to send payments, physical checks. Okay, so money can be measured with very high accuracy, right? If it's electronic record, and there is no limit how many decimals we can keep. Okay, and that, by the way, is one of the it's kind of not related to statistics, but one of the fraud techniques. I used to teach also accounting information systems, and we're talking about fraud, right? Computer crimes. So one form of the crime is something that's called salami slicing. So basically, salami slicing is, like, for example, if I'm a programmer and I'm building a piece of code that processes the transactions. Transactions are electronic, so therefore they can be rounded to the nearest decimals. Like, for example, you're buying gas, this 9/10 of a cent per gallon, right? You pump 20 gallons, you end up with like fraction of the cent. So if you round to the nearest cent, nobody will ever notice, right? So therefore you can basically take this fraction of the cent and transfer it somewhere, right? It's not a lot, but how many people are buying gas every day? A lot of people, right? So cent by cent you accumulate huge amounts of money. That's basically salami slicing, rounding to the nearest cent electronically, right? So money can be measured on the continuous range essentially, right? If we think about money as electronic record in the database, okay? All right, so let's talk about probability distributions. Probability distribution is, it can take many different forms, but essentially what it is we can connect a value of the random variable with the probability to observe that value of the random variable. So it can be given in terms of the table, or in form of the formula, or graph, or something like that, okay? So let's kind of discuss what is the probability, and then I'm going to give you a couple of examples of probability distributions for simple discrete random variable. Probability is a likelihood of something happening, right? And therefore, that something, we have to define what it is. So that's an event, okay? If I'm looking for something to happen, I'm expecting certain event. So probability is a measure of expectation, how likely it is for me to observe that event. For example, there is every day weather forecast gives you a chance of rain today, right? So we don't know, for example, today, seems to be pretty sunny outside, but there is still a chance that maybe somehow clouds will form in the atmosphere and we'll have a rain, right? So we don't know that with certainty. So today probably it's very low, maybe a 5% chance or 10% chance. But on the cloudy day, the chance of rain is higher, okay? So we don't know if it will happen or not. It just gives us the likelihood, how probable it is to expect, how likely it is to expect a rain to happen, for example. So event can be actually a combined event. So what does that mean? I'm looking for multiple outcomes to happen, and then I'm going to call it an event. For example, if I'm throwing a die, okay, die can land on 6 different sides, right? So I can get 6 different results. But if I'm looking for a 2 or a 4, that's an event for me. So either one of these two things is fine by me. So if I'm getting a 2 or a 4, that's a positive outcome. I call it a success. If I'm getting a 1, a 3, a 5, or a 6, that's not something that I'm expecting. So I'm going to call it a failure, right? So by a combination of 2 possibilities and 2 and a 4, I'm going to call a favorable outcome for me, okay? All right. So on this slide, basically, what I wanted to emphasize is, I told you that before, right? We're going to use capital letters to denote the probabilities. X, Y, Z, T for time, for example. Huh? Phil?
Can you go back to the last slide?
Sure. Huh?
What, for example, in the game of crash, what is the probability of 7, a sum of 7, 1 time and 2 rolls? So that's a 5 and a 2. Or is it just 1 die? You roll
Krebs? Krebs?
2 die.
Yeah, 2 dice, right?
So either 5 or 2 or 6 or 1.
Oh yeah, we're going to actually talk about that. Well, let's actually let's discuss this thing because that's a good question, right? A game of craps. I never was in casino, so I know this thing only by reading on the internet. That's it. So let me.
Fun game to play.
Yeah, apparently. Okay, hold on. Let me go ahead and show. All right, hold on. I'm going to show it on the same screen. Give me a sec. All right.
It's probably one of the most exciting games to play.
I'm guessing, yeah. I never went to the casino, so I don't want to even try because it may be addictive, right? Who knows? All right. So let's discuss the game of craps, right? So let's see if I can write. Okay. Yep.
So what's this program that you access?
Oh, this one is Microsoft Notes.
Do we have that in these computers?
No, that actually comes. Yeah. This is the Surface, right? So it's a touch screen, so it comes with a pen. But Node actually can be installed on regular machines, but you have to type it, of course, right? And then you probably can use the mouse to take the drawings, but this one is kind of simpler. So probability, we kind of discussed that, right? Probability. Probability is the likelihood of certain thing to happen, right? And there is a very simple formula. We actually used that formula already in the previous sections. Remember when we did the very first homework, customers visiting Red Lobster restaurant, right? We had 220 responses, and out of them, like, 48 were poor, etc., right? When we created the tabular summary, the program computed for us relative frequency, right? Or what it called probability, okay? So it said probability of response poor is 0.0769 or something like that. How it was computed. We had, like say, 48 responses poor out of 220 responses altogether, right? And that ratio is viewed as the probability. So therefore, the very simple elementary formula can go like that. It's the ratio of number of favorable outcomes, favorable outcomes divided by total number of outcomes. Total, number of outcomes. Okay, total number of outcomes. Okay? So that's basically how we can define probability from the general standpoint, right? So, for example, if I'm playing the game of craps, okay? How can I find, well, let's actually create a list first. So, game of craps is played with 2 dice, right? So you have die 1 and die 2, and they're equivalent. Every die has 6 sides. They're not loaded. They're not heavy on any side. So every outcome is equally likely, right? So I told you that probability distribution is a list of values that the variable can take and their corresponding probabilities, right? So here I'm going to have x, the list of all the values, right? And in the next column, I'm going to have probability of that x, okay? So when I'm throwing 2 dice together, okay, and I'm looking for the sum on the both dice, right? What's the smallest value it can take? The sum. 2, right? 2, and then I have a 3, and I have a 4, 5, 6, 7, 8. What's the highest? 12, right? 8, 9, 10, 11, and 12. Okay? Well, that's my comprehensive list. That's everything and anything that can happen, right? That's it. So if I'm using that formula right here, there are 2 ways actually how I can use that formula. Okay? Way number 1 is I can say, well, let's experiment, let's collect the data. Like in the case of restaurant, how can I know what's the likelihood of a randomly selected customer to rank my service as excellent? I can't just basically scratch my head and say, well, it seems like 11% chance. Where does that come from, right? I have to collect the data and analyze the data. So I have to get a sample, a number of customers, right? And then ask them. And then whoever answers excellent, I have to take only that count and divide by the total number of observations, right? So coming back to this dice example, right, game of craps, what I can do in order to find these probabilities is get 2 dice and spend a couple of days just throwing them, right? So I'll get like 10,000 throws, for example, okay? And out of these 10,000 throws, some of them would be sum of 2, 3, 4, etc., and then 12, right? And then I'm going to use this formula, right? I'm going to say, well, out of 10,000 throws, let's say, 361, I got 2s, right? So get 361 divided by 10,000, and that's your probability right there, okay? So that's one way to do it. Another way to do it is kind of use logic, okay? So let's use the logic. Let's say I'm looking for a 2 and using the same formula. So let's first find out what's that number, okay? Right there. Total number of possible outcomes. True or false? Every die is equally likely to land on either one of 6 sides. So therefore, when I'm throwing 1 die, likelihood, total number of combinations that I can get out of just 1 die is 6, right? Same applies to the second die, right? And second die is kind of independent from my first die. So therefore, that means that I throw the first die, it lands on one of the sides, and regardless of what happened with the first die, second side decides basically by itself, right, on its own, right? So for every one combination, for any possible outcome on die number 1, I can have 6 possibilities on die number 2, right? And on die number 1, I have 6 of these combinations, right? So total number of outcomes is 6 on die number 1, but for each one of these things, there are 6 possible outcomes on die number 2, right? So altogether, I'm looking 6 times 6, 36 possible combos, right? So there you go, 36. Okay, in how many different ways I can get a 2? There is only one way, right? 1 and 1, that's it, nothing else. So therefore, there is only one way. Number of possible, so here I'm talking about numerator, right? Number of favorable outcomes, okay? So there is only one way how can I get a 2, okay? It's 1 and 1. So therefore, the probability to get a 2 is 1 out of 36, right? One way out of 36 different ways how the dice can land, okay? So therefore, there you go. Here is your probability for the getting a 2 out of 2 dice, 1 out of 36, okay? So now let's, make sense? All right. Now let's erase that part. Now let's talk about 3, okay? Total number of outcomes still 36, right? It doesn't change ever, right? But now I'm talking about 3. So 3 I can get in what ways? I can get on die number 1 a 1 and 2 on die number 2, or alternatively I can get a 2 on the first one and 1 on the second one. So 2 ways out of 36, right? So therefore 2 out of 36, or 1 over 18, right? So likelihood of 3 is 2 out of 36. Well, let's do a couple of them, couple more, right? How can I get a 4 on 2 dice? It's 1 and 3, it's 2 and 2, and it's 3 and 1, right? So 3 ways out of 36. Do you see a pattern going on? 1 out of 36, 2 out of 36, and 3 out of 36. So it's increasing, right? 3 out of 36. Okay. Now let's actually come from a different end of the spectrum. Let's talk about 12, right? So I'm throwing 2 dice and I'm getting a sum of 12. In how many ways I can get that? Just one, right? It's 6 and 6, and that's it. Okay? So a 12 is 1 way out of 36. So therefore, on this end of the spectrum, I have 1 out of 36, right?
So 6 and 8 in the game of craps, that's the one. Those are the ones you want to bat most of the time.
Yeah, yeah. In the middle, they're most likely. Exactly. So let's take a look at 11, right? How can I get an 11? 11 is 5 and 6, or 6 and 5, right? And that's it. So 2 ways out of 36. So here I have 2 out of 36. So you can see that the other end of the spectrum looks a lot like the beginning, right? So therefore, I can just start filling in the numbers. Let me actually write it a little bit more compact. 2 out of 36. So here I have 3 out of 36. And here I have 4 out of 36. And this one is 4 out of 36, right? 6 is 5 out of 36. And so is 8. And it looks like 7 is 6 out of 36, and that's the most likely sum that you can throw in the game of craps, right? Let's kind of verify that just for the fun of it, right? So how can I get a 7? 7 is 1 and 6, right? And there is 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1, right? So 6 different ways out of 36. And that's basically what it says right there, right, for the 7. So probability, this is a probability distribution, ladies and gentlemen, okay? Allow me to introduce you to our new friend, probability distribution, okay? It's a table, right? It's basically a list of values that the variable can take, and every value is connected, linked with its corresponding probability. And notice that I didn't throw a single die in doing so, right? I didn't spend 2 days making 10,000 throws and using that formula. Instead of that, I used the logic, right?
So if you know the game of craps, the first roll, if you roll a 7 on the first roll, you win. If you don't roll a 7 on the first roll, then you bet, then you put your chips on 6 and 8. So you continue to roll. You notice that the probability is 5 and 5 or 6 and an 8. You continue to roll, and you land on a 6, you win. Lands on an 8, you win. But the next time you roll a 7, you lose.
Yeah.
That's why the casino typically always.
Oh yeah, casinos have.
Stay in the game long enough.
Yeah, well, play a game long enough. Yeah, the house will win, right, in the long run. And in the casino, actually, the odds are only slightly tipped in the favor of the casino. For example, it's called roulette, right? When you spin the roulette and you throw the ball, right, and it lands in one of the slots. How many slots are out there?
30. You mean a roulette table?
The roulette.
38 slots with one green and one green as a loser. It counts 0, 0, 2, so it's 38. I think it's 38.
38, and one of them, if it lands on the 0, then casino wins, right?
Yeah, you lose.
Yeah. So you basically, it's like let's say I put on even number, right? So if it lands on one of the even numbers, then I win. If it lands on the odd number, then I lose, right? But yeah, or red and black, right? So half and half, right? Essentially, right? So your chance of winning is 50%, chance of losing is 50%, right? But there is a 0, right? That's the casino win, right? So therefore, out of 38, you're winning in the 19 cases and you're losing in 19 cases, but there is one extra case when the casino wins. Yeah, exactly. So you're winning with the probability 19 out of 36, and you're losing with the probability 20 out of 36. So it's only slightly tipped in favor of the casino, but that slightly is enough for them to make tons of money and finance huge hotels with essentially free rooms, right, and everything. So Las Vegas is the living proof that the statistics works.
It's blackjack, because blackjack odds are 50.0000, some of 1 on your favor.
Mm-hmm.
The casino is 49.99999.
Yeah.
So that's the only game that's you as a better. But it's still on. Continue to play, you'll lose.
Oh, absolutely, yes. So your expected loss on every play is very small, actually. Casino does not want you, they don't want you to come in, quickly lose your money and go home disappointed, right? Because you're essentially paying, most people are probably visiting casinos not because they're expecting huge, gain, right? Huge win. They want an experience, right? So, and they want it to last, right? So therefore you play, you win some, you lose some. On average, you lose more than you win, right? But it happens over time, basically. So on every game, you're winning only small, amount of money, but you win anyway. Or you lose anyway, right? You lose only a small amount of money, but you lose anyway. So that's basically, they're in the entertainment business, right? At the same time, it's a business. But it's a statistical business, okay? So statistically, they're winning. Okay, in the long run, they do win. Okay, make sense? So that's basically an example of the probability distribution. And, even easier, even simpler when you throw one die, right? With one die, very obvious, right? So here's the list of x's, here's the list of probabilities. When you throw a die, you have only 6 outcomes, right? 4, 5, and 6. And it's equally likely, right? So therefore, what's the likelihood of getting a 1? Well, there's only one way to do it out of 6. Same applies to 2, right? So therefore, all of them are 1 out of 6, right? So with one die, it's all pretty much straightforward. Okay? So let's go back to the slides. All right. Okay. So let's actually talk about properties. That should be fairly straightforward. Properties of probability distributions for discrete distributions. Okay. So first of all, however we calculate or define probabilities, it has to be the number between 0 and 1 for any value of the random variable x, right? So likelihood cannot be 0, right? 0 means that you're looking at the event that will never happen, right? Probability 0, that means that you will never ever observe that. Probability of 1 means that this is certainty, right? You know precisely that this thing is going to happen, okay? Anything else in between is also possible. So probability has to be a number between 0 and 1. Another thing is, and we saw that before, right, with the example of, I believe, Red Lobster, right, that we did. Probabilities of customers giving us a rating of poor, fair, good, very good, and excellent. They all have to add up to 1, right? So that reflects, second property reflects the fact that I don't know what's going to happen, but something will happen for sure, right? So I'm throwing 2 dice. The probabilities range from 2 out of 36 all the way up to 6 out of 36 and then again down to 2 out of 36. When I throw a couple of dice, I don't know what sum I'm going to get, right? It can be 2, 3, 4, all the way up to 12, right? So one of them will happen for sure. And if you add, go back to the, this distribution we just created and add those probabilities, it's a really good bet that they will add up to 1. Okay, no pun intended, really good bet. That they will add up to 1. So all probabilities have to give you certainty, right? So sum equals to 100% or 1.0. Okay. Remember when we discussed the populations and samples, I told you that population is the holy grail of statistics, right? Statisticians love to have population at their fingertips. Why? Because you don't even have to guess about, what's the average purchase done by the customers, or what's the percentage of television viewers who watch Big Bang Theory on the TV every evening. If you have access to the full information about absolutely everybody, every single transaction, every single viewer, you don't have to guess. You can exactly compute all that you need, right? So having a population data at your disposal is holy grail of statistics. That's the golden target, okay? Well, what's even better than having a population is to know how the population is distributed. So knowing distribution of the population, if you have that knowledge, how distribution is, how the population is distributed, beats everything, okay? Because out of the distribution, you can compute everything that you need to know. And we'll see some examples today, okay? So, for example, average, right? If I know that, for example, if I know the probability distribution of my random variable, so everything that we discuss right now is about discrete random variables, right? So I know essentially P of x, right? Probability of every single value that I can get, okay? Then using that formula, I can compute the average, right? So all you have to do is multiply every x by its probability and add them all together, all right? So for example, let's actually give it a spin, right? Let me go back to the, okay, hold on. Again, I have to see what happens every time when I change the screens. It basically resets. I don't know why. So I'm going to show the display again. Okay. All right. So let's go back to our formula. Okay. So this is what happens when I throw one single die, right? Let's do pretty useless exercise. Okay. If I keep throwing the dice, okay, what is the average reading of the die that I can get? Well, one way to do it is, again, I take a die, right, and I spend a couple of days just throwing it and recording my results in big Excel file, okay? So throw number 1, I'll get a 2. Throw number 2, I'll get a 4, and then 5, and then 1, and then 2 again, 3, 6, 2, etc. Then at the end of the second day, I'll have like 10,000 throws. I'll just average them out and find out what's my average reading on the die that I can get, okay? Or alternatively, I can say, well, let's not do it, okay? Let's use the formula. So what's the average that I can get? Well, according to the formula, it's add together x's multiplied by their probabilities, right, across all different possibilities, okay? And that would be what? I can get a 1 with the probability 1 out of 6. Or I can get a 2 with the probability 1 out of 6. Or I can get a 3 with the same probability. And the last one is going to be I can get a 6 with the probability 1 out of 6, right? So it looks like 1 out of 6 is the common multiplier, right? And I have to multiply that by sum of 1 through 6. What's the sum of 1 through 6? Let's see. 1 plus 6 is 3, plus 3. 1 plus 2 is 3, right? Plus 3 is 6, plus 4 is 10, then 15, and then 21, right? Looks like it's 21 divided by 6. So therefore, it's 3 and 3/6, or 3.5. Okay? That, of course, I mean, that can be misleading. So that's actually a good example to illustrate that. Okay? So if I choose to actually perform the experiment and throw the die many times, right, then I'm going to end up with a bunch of numbers, and if I average them out, I'm not going to get exactly 3.5, but very close, right? The more I throw, the closer it gets to 3.5 probably, okay? So my average reading on the die is 3.5, but note that it's not one of the readings, right? 3.5 is kind of in between from 3 to 4, right? Die cannot stand on one of its edges, right? Kind of in the mid-air, sort of, right? So it's not quite 3 and not quite 5, so let's not quite 4, and let's call it 3.5. No, of course that's not what's happening, okay? So 3.5, we don't round it up or down, that's just average, okay? Long run average for our experiment. But in order to find that, I don't even need to collect the data. All I have to do is, if I know the distribution, I can use that formula and find my average. You see how valuable it is to know the distribution? I don't even know to collect the data, to throw the dice, to spend my time. I know the distribution, I can compute the mean. Same thing, actually, very similar formula. It's not part of the slides, but anyway. If I want to compute the variance, sigma squared, okay? If I know the distribution, very simple thing to do, okay? Again, it's sum across all the possible outcomes. All I have to do is take the x, subtract xi, any possible value of my variable, subtract the mean, square that, and multiply that by the probability of that x. Okay? So if I know the distribution, essentially probability of every possible x, first thing, just like what we did right now, right? I can compute the mean, and after that, knowing the mean, I can apply this formula and compute the variance. So from the variance, I can compute the standard deviation. So knowing the probability distribution beats having the access to the population data, because you can compute everything that you need. All measures, okay? You can compute mode, mean, median, range, if there is a range, right? Standard deviation, variance, different percentiles, interquartile range, all these things that we have discussed yesterday when we talked about numerical descriptive statistics, right? Knowing probability distribution is a very good thing in statistics, okay? Unfortunately, that doesn't happen very frequently, okay? More often than not, you don't know that, right? Okay, so let's see. Do you want to take a break here for 10 minutes and then we'll continue? All right. All right, now let's discuss the specific discrete distribution, which actually plays a pretty important role in statistics, okay? It's called binomial distribution. What's a binomial distribution? Well, when you hear the word bi means two, right? So it's a two-nomial distribution. The reason why it's called binomial is because we really, this distribution is based on the idea of a trial, or sometimes it's called an experiment, okay? Trial is something, some action that we try over and over and over again. And the assumption behind the binomial distribution is that every time when we run a trial or perform this action, this experiment, it can result in two possible outcomes. And we randomly label one of them to be called success, and another of them, well, what's the opposite of success? It's a failure. So therefore, there are only two possibilities, success or failure. Every possibility, we're going to assign probability to that. Okay, so a standard way to think about a success and a failure is to say that success happens on every trial with the probability of small p, and failure with the probability of 1 minus small p, because there are only two options, right? Success or failure. The probabilities obviously have to add up to 1, right? I either succeed in the trial or I fail. So therefore, if probability of success is p, probability of the failure is whatever is left, 1 minus p, that is, right? So there are several conditions that you have to satisfy in order for your bunch of trials to qualify as the binomial experiment, and therefore follow the binomial distribution, okay? So first of all, we have to know how many trials we perform. So, for example, flipping a coin, okay? Flipping a coin, when you flip a coin, it can be either heads or tails, right? So you can consider flipping coin one time a binomial trial, because only two possibilities. And if it's a fair coin, of course, probability of success is 50%, probability of failure is another 50%, right? So we have to know, for the experiment to be a binomial experiment, we have to know how many trials we do. So if I flip a coin 10 times, that would be my n, right? I perform the same trial 10 times. Every trial has two possibilities, success or failure. We know right up front, right off the bat, what's the probability on each trial to result in a success, and the probability 1 minus p for each trial to result in a failure. And another important distinction is that trials have to be independent from each other, which is true for the coin example, right? Because coin doesn't have a memory, right? So 50-50 means what? Half of the time I should get heads, right? And half of the time I should get tails. So they should balance each other, right? In the long run. For me, to make sense, for example, if I flip a coin once, I'm getting tails. So I'm thinking, well, this should be balanced. So next flip probably is going to be heads, right? Because it should balance each other. No, doesn't happen that way. Still probability, even if I'm getting a tails right now, tails on the next one, tails on the next one, I'm thinking, wow, that's a lot of tails in a row. So I accumulated enough trials, right, to get definitely heads next time. No, still 50-50. Coin has no memory. Coin doesn't remember what happened in the past, okay? If you keep getting a lot of heads, that doesn't mean that the next one is going to be tails, right? So trials are independent from each other, okay? So that's an important distinction. All right, now note that the random variable really, in this case, is how many successes I'm going to get out of n trials. So if I'm flipping a coin 10 times, how many, let's say, first I have to define success, right? What's a success? Let's say if I'm getting a tails, that's a success for me, okay? And I decide to flip a coin 10 times. How many tails can I get out of 10 flips at minimum? What's the smallest number that I can get? None, right? I flip 10 times the coin and all 10 are heads. No successes, zeros, that's the minimum number, right? What's the highest number of successes that I can get out of 10 flips? 10, right? All of them are tails. Anything else in between is also a possibility, right? It can be 50-50, 5 tails, 5 heads. It can be 70-30 or 30-70, 60-40, etc. So my random variable really is how many successes I'm getting out of n trials, right? And I don't know that number. I flip coin 10 times, I get 2 tails and 8 heads, so 2 successes, right? And then I say, let's do it again. I perform same 10 flips, and now I'm getting 7 tails and 3 heads, right? So number of tails, what I defined as a success, is different every time when I flip the coin 10 times, okay? So the random variable really here is how many successes you can get out of n flips, and you decided on n flips from the get-go, okay? So there is no stigma or judgment attached to definition of what success or failure. I can always redefine success and failure and make it, other way around, right? So what I used to call success now becomes a failure. So there is no really, like I said, judgment attached to that, okay? The success can be a combined event. So for example, flipping a die, right? Rolling a die. If I call, for example, 1 or 4 a success, right? I'm rolling a die 1 time, and if I'm getting a 1 or a 4, that's what I'm looking for, okay? So that is a success. If I'm getting anything else, it can be 2, 3, 5, or 6, well, that's a failure, okay? So what's the probability of success in this case? Well, if I'm getting a 1, the likelihood of that is 1/6, right? If I'm getting a 4, it's another 1/6, so 1 or another, that's 2 possibilities out of 6 possibilities, right? Remember our formula that we used in the previous part. Number of favorable outcomes divided by the total number of outcomes, right? So one die being rolled, 6 possible outcomes, and only 2 result in success, 1 and 4, right? So 2 out of 6, 1/3 is my probability of success. So therefore 2/3 is the probability of not getting 1 or 4, and that's a failure, okay? Binomial distribution actually is very practical, and we're going to look at some examples later during this semester. That's how actually political polls are being run during the election. The underlying distribution, every time one TV station makes an estimation during the election, who is going to win the state of Michigan or state of Virginia, they're collecting poll exit data, right? So people coming out of the voting booths, they're asking them, who did you vote for, Republican or Democratic candidate? And the assumption here is that every time when you ask a person, whom did you vote for, that's a trial, right? and it can result in one of the two outcomes. It's either Republican or Democratic candidate. Okay. Also, trials are independent. Why is that? Well, because let's say there is one person coming out of the voting place, right? They just voted. I ask them and they say, I voted for Republican. Does that mean that the next one probably is going to vote for a Democrat? No, right? They're different people, probably not even related, don't know each other, right? Male or female, whatever it might be. So one voting person does not affect the next voting person. So my trials, every time when I ask, whom did you vote for? Trials are independent. So I'm truly dealing with the binomial trials here, right? Every time when I ask somebody, whom did they vote for? They should be governed, the process of voting should be governed by the underlying binomial distribution, okay? All right, flipping a coin, well, we discussed that already, right? So I'm not going to repeat that again. Flipping a coin 10 times, etc., etc. Okay, let's do an example. And actually this is a good example. I'm going to assign homework actually, and in the homework, I will ask you to do pretty much what we're going to do right now. And that is compute certain probabilities by hand, just to kind of have an experience with the underlying formula. Okay? So first, let's take a look at this example, and then we'll do that manually. Okay? So there is a hard way to find the probability, and then there is an easy way. Easy way is the one with jump, right? Hard way is manual. So we'll do one example, one of these questions manually, and then after that we'll see what jump does. Okay? John Doe is a student taking this class, BSN 231, statistics, and John's strategy is to not study, but rely on blind luck for the next quiz. So quiz, yeah, some students do that, not a lot, but yeah, some historically had some of these. The quiz consists of 10 multiple choice questions. Each question has 5 possible answers, and of course one of them is correct, 4 of them are wrong, right? So John plans to kind of pursue his odds, right? Not study, but just guess. The answer is always C, something like that, right? It's like Hitchhiker's Guide to the Galaxy, if you've seen that movie, right? What's the meaning of life, universe, and everything, right? The meaning of life is 42, right? Yeah, so same thing here. Yeah, the answer is always C, okay? So you bubble in C, sometimes you get it, sometimes you don't get it. So what's the likelihood that John gets not a single answer correctly? That's probably not going to happen, but there is a possibility, right? He tried to guess 10 questions, didn't get any one single of them, right? What's the probability that he gets exactly 2 questions correctly? And what's the probability that he fails the quiz, guesses correctly less than 7 questions? So 6 or 5 or 4, 3, 2, 1, or 0, right? Okay, so let's do this. First of all, let's kind of discuss and realize that this is actually a binomial process, right? So first of all, what's a trial in our example? Well, he has 10 questions. Every question is a hit or a miss, right? So attempting to correctly guess an answer on one single question is a trial, right? So you bubble in C, because all of them are C's, right? You either get it or you don't, okay? So what's the probability of successfully guessing a question? Well, there are 5 answers, right? So 1 out of 5, right? You pick C, it's 1 out of 5 possibilities. Again, using our formula, right? Number of favorable divided by the total. There is only one outcome that's favorable, so 1 out of 5. That's your likelihood to get it right, 20%, 0.2. And therefore, 1 minus 0.2, 0.8, that's the likelihood to get the question wrong, right? So every question, he actually much more likely, 4 times more likely to get it wrong than to get it right. And also, trials are independent. Why is that? Well, if I answer C on question number 1, what does that tell me about question number 2? Nothing, right? Because typically, instructors like myself, we scramble the answers, right? So if the answer on the previous one was C, it can be C on the next one as well, but it can be something else, right? We try to randomize them, okay? So, but actually what happens in my classes, sometimes I basically do that on purpose. I'm like a streak of the same answers. So the answer is B, 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 B. So yeah, students look at that and like, wow, it can be right. They should be all over the place, right? And I see the pattern here. So I do that sometimes just to kind of throw off balance. All right, anyhow, but if professors are not sneaky like me and they truly randomize it, right, then answers really are independent from each other, right? So because the previous one, the answer was A, that doesn't mean that the next one is going to be A or not A. That, again, it's random, right? So we're dealing with the binomial process here. Okay. So let me switch over to note-taking application, and again, it doesn't show up on my main screen. Okay, hold on. I'm going to again do this. Okay. Changes. All right. All right. So, new page. Remember we discussed that probability distribution is just a list of values for the random variable and their corresponding probabilities, right? So you can find probabilities in a couple of different ways. You can first of all conduct the experiment. Throw the die 10,000 times and figure out probability over 1, over 2, etc., right? Or you can use logic like we did in the example of 2 dice, right? How can you get a 3? In 2 different ways. 1 and 2, 2 and 1 out of 36, that gives you the probability. Or there is a formula underlying, okay, the distribution. And that's the case with binomial distribution. Binomial distribution has a formula, and here it is. Okay, probability to get exactly X number of successes is given by relatively simple formula. N is the number of my trials, right? How many times I attempt the same thing over and over and over again. And choose X. Choose X. And that tells me in how many different ways I can choose X elements out of total of N elements, okay? And out of these N trials, X should be number of successes, right? Because that's what variable is, random variable. How many successes I can get out of N attempts, okay? Every success happens with a probability of P, right? And because successes are independent, I have to multiply them, right? So therefore, it makes P to the power of X, number of successes. And I also have, the rest of them are failures, right? So failure happens with a probability of 1 minus P. So I have to raise that to the power of N minus X, okay? So that's basically general formula that we're going to use. And by the way, N choose X is also, it has a formula. N choose X. The formula for that is N factorial, N with an exclamation point, divided by X factorial, N minus X factorial. Okay? Do you remember what's factorial from math classes that you took before? Yep. Factorial is product of all integers starting from 1 and ending in whatever it is you're trying to factorize, right? So for example, 5 factorial, oh, that's not connected, right? 5 factorial is product of 1 times 2 times 3 times 4 times 5, okay? So, for example, let's compute one of the questions that we had on the PowerPoint is try and compute the probability of this student, John, getting exactly 2 questions out of 10 correctly and therefore 8 questions incorrectly, right? So I'm looking to find the probability that number of correctly guessed questions is equal to precisely 2. Okay? All right, so according to my formula, it should be 10, right? Because there are 10 questions on the quiz. He's trying 10 questions. From N, I have to choose 2 which answers correctly. And the reason for that actually is the combination of 2 questions that he gets correctly can be anything, right? It can be number 1 and number 2, and the rest are wrong, or it can be number 3 and number 7, or number 5 and 10. So any combination, right? So that basically gives me all possibilities. How out of 10 questions I can choose 2 that he gets correctly. The rest of them are wrong. Okay, so then I have to multiply it by probability of correct. Answer is 20%, and here he gets only 2 of them correctly, right? So 0.2 squared. and then probability of getting incorrectly a question is 80%, and he gets 8 of them incorrect, right? Out of 10. 10 minus 2 is 8. Okay. So let's now take a look at this number right here and choose 2. According to my formula, that should be 10 factorial, right? So I'm using that formula right here now. It should be 10 factorial divided by 2 factorial. Okay. And 10 minus 2, this part, is 8. 8 factorial. All right? So let me write it out explicitly. It's 1 times 2 times 3 times ... Now I'm going to have 7, 8, 9, and 10, right? And divided by 2 factorial is just 1 times 2, nothing more, right? And I have to multiply it by 8 factorial. So that means 1 times 2 times 3 times 7 times 8. Okay? So as you can see, this part and this part, they cancel out. And all I have is 90 divided by 2, which is 45. So out of 10 questions, I can choose 2 that he gets correctly in 45 different ways. That's basically what it says. Okay? So probability, therefore, coming back to my original question, right? What's the probability that he gets he gets exactly 2 questions correctly? Okay? That's going to be n choose x, 10 choose 2, that is 45, right? Multiplied by, what's 0.2 squared? It's 0.04, correct? Yep, and I can do 0.8 to the power of 8 in my mind, so I'm just going to leave it like that. Okay? So that's the probability numerically. Now let's use actually Excel, probably, right? So let's switch over, go back to the screen, and now I'm going to use just Excel in order to calculate the probability. All right? Let me make it bigger. All right. So here I'm going to just type the formula. Right? 45, that my 10 choose 2, okay, multiplied by 0.2 squared, that was 0.04, and multiplied by, how do I raise a number to the power of 8? Well, there is a function in Excel, right? Power function. Number 0.8 is being raised to the power 8. Okay? And when I hit enter, here is my answer, right? So the likelihood that John, who does not study statistics, relies purely on blind luck, gets precisely 2 questions correctly and 8 questions he completely misses, the likelihood of that is 302, right? 30.2% essentially, that's what it says, right? 30.2%. Okay? So that's a long way to do the probability. And like I said, you have one simple problem like that on your homework that I will assign today. Okay? Now let's take a look at how JUMP does that. All right? So we should get the same answer, right? Essentially, and then be able to answer some other questions as well. So I'm going to hide that part and start JUMP. Okay? Now JUMP, IT was supposed to actually update JUMP on these computers yesterday, and let's see if they did. Here is basically how you calculate the probabilities in JUMP. Okay? All you have to do is go to Help menu, and in the Help menu there is an option that says Sample Data. You see that one? Sample Data. Okay, so let's click Sample Data. And that's actually a pretty good collection of teaching tools, as it turns out. We're going to use some of them later on. So for example, tomorrow when we'll talk about the central limit theorem and sampling distribution, there is a really nice animation that's built into JUMP that shows you basically how the sampling distribution is being formed when you're getting samples and averaging them out, etc., etc. So teaching script, you see that option under the teaching resources. There is a teaching script. Click on that, expand it, and interactive teaching modules. So let's see if they really updated JUMP yesterday. If you expand that, there is a lot of different options, right? and one of them says distribution calculator. You find it? Distribution calculator. So go ahead and open it up, and it gives you immediately that. Okay, so it starts with normal distribution. We're actually going to talk about normal distribution later on today. Okay. Now, what we're looking for is binomial, right? So go ahead and click on the list of distributions, and it should show you a bunch of them, right? So I'm going to pick binomial. And when I pick binomial, the picture changes, right? Did it change for you? Okay, so they did update jump. Good. All right, now, first of all, binomial distribution. Remember we discussed that there are a few things going on, right? First of all, you need to know how many trials you perform, how many times you flip the coin, right? Or how many questions this student attempted during the quiz, right? Number of trials. So that's one thing, that's one parameter that you enter. Another thing that you need to know about binomial distribution is what's the likelihood of success on each trial, right? What's the probability to get a tails on a flip? Or what's the probability to get a question correctly when you attempt to randomly guess the answer, okay? So there are two things that you need to specify for the binomial distribution. N, number of trials, and P, probability of success. And that's what it says up there, right? Two parameters. So what do I enter for the probability of success? 0.2, right? 20% chance of getting the question right. And how many questions he attempts? 10 questions. So as we enter things, you can see that it shows me the distribution. And basically, remember we discussed that. How many successes can we have out of n trials, right? How many questions he can get correctly. Smallest number it can be is 0. And you can see that this is where your distribution starts, right? The highest number it can be is 10. This is where the distribution ends. And everything else in between is possible, okay? So how do I get... So here's the part where I have to compute the probability of exactly 2. We know the answer already, right? We just computed that manually. It's 0.30199 or 0.302, right, if you round that. Okay, so it looks like I need to use this option, right? X larger than lower boundary and less than or equal to the upper boundary. So how do I get exactly number 2? My upper boundary should be 2, right? Less than or equal to 2. What should be my lower boundary? It should be 1, right? That's basically how it's structured. Greater than a number, less than or equal to a number. If it's greater than 1, but less than or equal to 2, that means 2 exactly, right? And you can see that at the bottom, it calculates the probability for me, right there. First of all, this is the bar that corresponds to the probability, right? Highlighted in my distribution. And the answer is 0.302. That's exactly what we computed, right? I'm looking to answer this question, right? What's the, hold on, where's my problem? Here, right? What is the probability that John gets exactly 2 answers correctly, right? And we computed that already, just 1 second ago, right? So how do I get that to work in jump? Well, I have to work with these options, right? Less than a number, or greater than a number, or in the range, or outside the range, right? That's basically, these are your options, okay? Now how can it doesn't give me the option to compute exactly the number, right? Probability of precisely 2. So I have to work with these options. The closest that I can come to that is this one, right? It's greater than 1, but less than or equal to 2. And because it's discrete greater than 1, the next thing is 2, right? So it's 2 or 2, right? So that means that precisely 2. Make sense? It's kind of a little bit tricky, right? Just a little bit, but yeah, we can get it to work. Greater than 1, but less than or equal to 2. That makes it precisely 2. Okay?
So what's the probability of being 4 answers correct to be 4 and 1?
A probability of exactly 4 answers? 3 and 4, right? Greater than 3, but less than or equal to 4, right? So greater than 3, so here we have to type 3. But, oops, so yeah, it says you can't do that. Okay, so first you have to set up the higher limit, right? And then adjust the lower limit. Okay, yeah, 3 to 4, and there it is. So probability of precisely 4 is almost 9%, right there. Uh-huh.
So what if you wanted to get the probability that it gets 5 or more? Would you use the X greater than
5 or more? Yep. Probability of greater than, so 5 or more means greater than 4, right?
So it automatically changes it to 1
Yep. So it's smart enough, right, to recognize how many inputs you need, right? It's only one value, or do you have a range between x and y? That can be hard to explain?
You have to explain, yeah.
Oh.
Understand.
Yeah. Oh, it's kind of similar to Visa, right? Or it's somewhat similar to Visa. Yeah. All right, so let's answer other questions. What's the probability that John gets no answers correctly? So he misses every single one of them. That's probably not likely, but what do I do here? Less than or equal to, probably, right? Less than or equal to 0, right? 0 or less. Well, there is nothing less than 0, so it's exactly 0. And that basically highlights the one bar for me, right? So likelihood that he bombs the quiz completely, right? Not a single correctly answered question, 0 successes, is actually not that small, close to 11%, 10.74% chance, right, of that happening. Make sense?
So what we probably got at least 5 questions right.
At least 5 means 5 or more, right? Yeah, greater than 4, exactly. Yeah, greater than 4, that's at least 5, right? So if you put greater than 4, so you can see that, right? All these bars are highlighted, 5 or more. Yeah, and so let's actually, this whole story has a point, okay? There is a moral value in all that, and that, here comes the punchline, right? What is the likelihood that John bombs the quiz, fails the quiz, right? Fails the quiz means less than 70% on the quiz. 6 questions correctly, or 5, or 4, or 0, right? Well, that will require actually adding together probability of 0, 1, 2, 3, etc., right? We don't want to do all this manual work, right? So let's actually turn to jump. So less than 7 means what? Less than or equal to 6, right? That's what I need to do. He gets less than 7 means 6 or less, correctly, right? And drum roll, what do you see? There is nearly 100% chance of failing, okay? So the moral of the story is don't rely on luck when it comes to education, okay? Study. Luck will not take you too far. There is 99.91% chance that you will not get the needed bare minimum just to pass the quiz, okay? Studying does help. All right, that's the only way. Make sense? Okay. So, go ahead.
Can you say which calculator it is again? I'm trying to write it down.
Sure. Here. How to get there, right? Yep. So you go to help. You go to sample data. All right. And teaching scripts. Yep. You expand teaching scripts. Interactive teaching modules. And in this list you find distribution calculator, right? And that's basically everything that you possibly, there are a lot of distributions. We're not going to go through all of them. In fact, that's pretty much it for discrete distributions. There is another very popular distribution that we use actually in operations management class, which is called, it's, I believe at the end, Poisson distribution. Poisson distribution actually is popular in operations management because it's used typically to model the process of customer arrivals or customer services. Okay? So things like waiting lines oftentimes are modeled using the Poisson distribution. So that, talking about earlier example with grocery stores such as Harris Teeter, right? How many customers come in every hour? We don't know, it's a random variable. Oftentimes what operations management people do is they model the arrival process as the Poisson distribution. So the random variable is how many customers arrive per hour, and it takes only one parameter, it's the average arrival rate. For example, if I have 50 customers arrive on average, there is a distribution that is centered around the number 50, actually. Okay? And the same applies to the service rate. So, for example, when it comes to service, customers browse by themselves, but the store's part is when it comes to the checkout process, right? So when you join the line to the checkout counter, when they scan your items and tell you the total, when you pay and you leave, that process takes different amount of time, right? Because somebody buys just 2 items, quick, right? Somebody buys the full cart of groceries, so there is a distribution. How long does it take to service one customer? So therefore, number of customers serviced by the checkout counter on average, it's also a variable, right? From hour to hour, it's a different number because different customers buy different amount of time items, right? So again, Poisson distribution is used to model oftentimes the service process. And that's how the waiting lines are being analyzed. But you will see that later in the course 304, operations management. There is a separate topic and formulas dedicated to waiting lines management. So, but in this part of this class, statistics, we're going to talk primarily and exclusively about the binomial distribution out of all possible discrete distributions. Okay? So pretty much done with discrete distributions. Do you have any questions? Concerns, complaints, sarcastic comments? All right. So let's now switch gears a little bit and let's talk about continuous distributions. Okay, now let's discuss continuous random variables. We talked briefly about continuous random variables, right? So today specifically we're going to look at the celebrity of the continuous, or celebrity of statistics actually. Remember, we kind of mentioned that distribution already. I told you that the most famous distribution in statistics starts with N, normal distribution. The reason for that we will discuss tomorrow, and it's called central limit theorem. But today we're going to just start learning about normal distribution. So continuous probability distributions. Before we get to the normal, let's talk in general about the continuous distributions. Continuous numbers, they're not discrete, right? So there is no distinction between two neighboring numbers. I mean, there are infinitely not. I said it wrong. There is there is no distinction. There are infinitely many numbers, right? Even in a very narrow interval, for example, between 0 and 1, there are infinitely many numbers. Okay? So if I'm measuring temperature or time or length or weight, any one of these things can be measured with killing accuracy, right? Down to very high decimal points. Okay? So essentially we can think that the range of possibilities for each continuously distributed variable is infinitely large. That means that the probability of every single observation is actually very, very infinitely small, right? So in the previous part that when we consider discrete variables, such as how many times you can get, heads out of 10 coin flips, or how many questions you can answer correctly on the quiz. We had finite number of choices, right? Out of 10 questions, you can answer correctly 0, 1, 2, 3, 4, etc., all the way up to 10, right? These were our choices. With continuous variables, such as measurement of weight, length, temperature outside, there are infinitely many possibilities. So therefore, every time when we ask a question, for example, what's the probability that it will take precisely 5 minutes to complete certain task? Okay? What's the likelihood, for example, that a cashier on the checkout counter will take precisely 1 minute to check out the customer? Likelihood of this event is 0, because time can be measured with killing accuracy. So the likelihood that it's going to take precisely, exactly, not more, not less than 1 minute, 60 seconds, that will probably never happen. It will get very close to 60 seconds, but you will never see exactly 60 seconds with killing accuracy. Okay, the likelihood of that is 0. But it makes sense to talk about probabilities of values for the continuous random variable within ranges between A and B, less than A, greater than B. These kind of probabilities, they can be computed. Now, every continuous variable comes with the probability density function, PDF. Okay? What's a probability density function? Loosely speaking, it's equivalent of what we had before, probability of event, or of a value x, right? But before we had discrete random variables, so we were looking at probabilities of discrete values. So here the probability density function, loosely speaking, it's actually not the right interpretation, but loosely speaking, it tells you for each, it gives you the value for each specific, it gives you the, certain value, it's not a probability, for each specific value of your continuous random variable, okay? So typically it's a formula, and just like we had before, for the discrete random variables, for continuous random variables, there should be certain rules that are in place, right? But first of all, remember our rule that probability should be between 0 and 1, right? Well, that's not quite the case for the PDF function, because PDF is not the probability. The function can get really, really high, okay? So it can exceed 1, because the interpretation of PDF is not exactly the probability of that specific value of the continuous random variable. The only restriction that we have is that the PDF should be greater than 0 or equal to 0, okay? Also, the total area under the curve should be exactly 1.0. That is equivalent of the rule that we had before. All probabilities should add up to 1, right? We don't know what event will happen. We don't know how many questions the student will get correctly on the quiz, but all different outcomes, if we compute their probabilities and add them together, that should add up to 1, giving us certainty. We don't know what will happen, but something will certainly happen, okay? Same thing here. The area, total area under the curve should be 1.0, and that is the same rule, equivalent of the rule that all probabilities should add up to 1. So these are only two restrictions. PDF should be 0 or more, and the total area under the curve should be 1. Okay? So therefore, it kind of gives you the hint, kind of, right? Let's go to the previous slide. Kind of gives you the hint that now we're looking at the probabilities as areas under the curve, right? And I'll have a slide actually later on that demonstrates that. So here is the celebrity in the world of statistics, okay, normal distribution. Here is the chart of the normal distribution, schematic representation. You can see that first of all, it's a symmetric distribution, right? Right side and left side look like a near reflection of each other. Unimodal, there is only one peak, and it goes to 0, or very, very close to 0, right, on minus and plus infinity. And also you can see that the range of the normal distribution is infinite, right? So it extends to the left to minus infinity and to the right to plus infinity. It approaches the horizontal line very, very closely, but never touches that, okay? So every time when you have a value, no matter how large or how small it is, there will be some area in the left tail or in the right tail of the distribution. The area can be very, very small, but it's not exactly 0, okay? All right, now this slide basically tells you that in order to specify fully normal distribution, you need two numbers. It takes two parameters, okay? One of them is mean. Mean, going back to the previous slide, right? Mean tells you the location of the peak of the distribution, the mode, okay? And the standard deviation tells you how wide is the distribution. Remember we discussed standard deviation as the measure of variability yesterday, right? What did we say? When sigma, standard deviation is high, variability is high, right? When sigma is low, variability is small. So therefore distribution looks more concentrated, more together, right? So it does not have a lot of scattering around the value of the mean, okay? Now, let me illustrate that with one very cool site. Okay, hold on. I'm gonna gain just my screen so that it shows up on the projector. Okay. All right. So here is the website that I discovered recently. Seeing theory. It's actually from Brown University. Apparently it was developed by faculty, maybe, at Brown University. And it's actually very good site to illustrate some of the concepts that we're going to talk about. Okay? So specifically, I want to illustrate for you the distribution. Okay? Normal distribution. And I'm going to post that online, by the way, the link to this site. So here is the section that talks about discrete and continuous distributions. All right, continuous, right? The normal distribution is continuous. So therefore, I have to pick continuous. And from the list, I'm going to select normal distribution. All right, so we just discussed that normal distribution takes two numbers, right? One of them is the position of the peak, mean. Another is sigma, standard deviation, which tells you how wide is the distribution. All right, so what I have here, well, a couple of sliders, right? One slider tells me where the mean is located. So right now it's 0 and the standard deviation is 1, okay? So I'm going to keep standard deviation the same. Sigma doesn't change that. I'm not going to change that, but slide the mean to the right and to the left. So what happens as I slide the mean? The distribution shape stays the same, right? Does not change how wide it is. It just basically changes the position of the peak. So right now I'm sitting at, can I get a 2? Yeah, cannot, apparently. Exactly 2. So minus 2.14, right? So as I slide the mean, the position of the peak changes, right? Now let's take a look at what happens if I start changing the standard deviation. So I'm going to go reset this thing. All right, so right now my standard deviation is 1. What will happen if I increase standard deviation? What do you think? It will get wider, right? The distribution will get wider. And look at the peak. So right now, the peak basically sits at approximately, what, 0.4, right, of the distribution. And as I increase the standard deviation, you can see that the distribution is getting flatter and flatter and flatter. And what happens with the peak? Peak is getting lower, right? Why that happens? What do you think? Because of the second rule, right? The total area under the curve should remain equal to 1, right? If my distribution is getting wider, it should get less tall, right? So it's getting kind of squished a little bit, but the total area remains pretty much, well, not pretty much the same, exactly equal to 1, right? Total area under the curve should always be equal to 1, no matter what. What will happen if I compress the distribution, make standard deviation smaller? It will start looking sharper and sharper, right? Well, let's do that. So my standard deviation is getting smaller, and standard deviation is the measure of variability or inconsistency, right? Small standard deviation means the data is more and more concentrated around the mean, right? And look what happens as I reach even higher. Like right now I have 0.3, right? And my distribution went outside of the picture, right? So here. The peak is very sharp, right? It looks very sharp. So you can see that right now my peak is sitting actually above 1.0, right? So therefore, to emphasize my previous point, the values on this curve, the numbers that this curve corresponds to on the y-axis, they're not probabilities, right? Because probability cannot exceed 1, and right now it does, right? At the peak I have more than 1. So it's not probability per se. Okay? But the area under the curve, or within certain limits, that's what gives me the probability. Okay? So standard deviation gets smaller, I get more and more concentrated distribution. If it gets higher, I get more and more flat distribution. Right? Okay. Good. So let's go back to the slides. All right. There it is. So these couple of slides, they basically illustrate pretty much what I was trying to emphasize. Right? Normal distribution, if you start changing the mean, the shape of the distribution does not change, but the peak moves to the right or to the left. But as you start changing the standard deviation, depending on which direction you're going, it's going to look more flat and spread to the right and to the left, or more sharp and concentrated around the mean. But again, you need to specify for the normal distribution 2 parameters, okay? Mean and the standard deviation. I ask seniors the same question in my data analytics class. Not all of them remember that fact, okay? So for the normal distribution, you need 2 parameters. Mean, the position of the peak, and standard deviation, how spread the distribution is to the right and to the left. Okay, calculating normal probabilities. As we discussed, probabilities are areas under the curve, right? So let's give it a business spin, right? So how many of you heard about a company called Dell? Everybody, right? What Dell does is they assemble computers, right? They're not really a production company per se. They don't manufacture parts, right? They buy parts from suppliers. They buy chips, processors from who? What are the two major companies that make computer chips? And Intel, and another one, the one you should know that. AMD, right? AMD, right? Two competitors, right? So there is a good bet if you buy a laptop or a desktop, the chip inside is from one of these two manufacturers, right? So they buy chips from Intel or AMD. They buy monitors from Sony, for example, right? They buy motherboard from Asus Tech or China Tech or Gigabyte. They buy memory from Kingston or Samsung, right? So whoever makes the memory. And all they do basically, Dell, is they assemble computers together and install software on that, right? And then it's ready to go. Okay, so they process a lot of orders per day, right? On their assembly operation. And different computers take different amount of time to manufacture. There is a variability. Why do you think there is a variability in the manufacturing process? Why isn't that? I mean, it's a standard thing, right? Take a box, put a motherboard in, plug in the CPU, memory, hard drive, down. Next. So what's making these things are so variable? One computer takes different amount of time to manufacture than another one. What do you think?
Different models?
Different models, right? It can require different parts. It takes time to deliver them from the warehouse. Sometimes they run out of parts, so they have to stop manufacturing, right? So there is a delay, right? Maybe one computer has extra features. The customer required 2 hard drives, right? Extra memory. They need to run more testing on the computer. Just make sure that it's running, right? So more configuration, more installation. Some customer wanted to install, certain software to be installed. So different computers take different amount of time to assemble and configure. And let's say that Dell tracked number of their computers. How long does it take from the first step on the assembly line until the last step when computer is ready to go, tested and boxed up? Okay, and they basically collected a bunch of data on a bunch of computers. Then they plot the histogram, let's say, and they looked at the shape of the histogram and said, "Ooh, look at that! The histogram looks PDN, pretty darn normal, right?" And then they said, "Well, if it looks normal, let's use normal distribution as a modeling tool." It's not exactly normal, right? Not a single thing in this universe, in the real world, is normally distributed. It's just an idealization, okay? But let's say that they plot the histogram and it looks very normal to them. And they say, let's use normal distribution. So what's the mean? Well, suppose that they found that the mean across all the computers was 50 minutes, okay? And the standard deviation is 10. Oh, by the way, that's basically a notation, okay? There are 2 ways how statisticians write out something is normally distributed. There is a long way to write out, so I'm going to write it on the board. Time to assemble a computer. Time to assemble a computer is normally distributed. Normally distributed with mean of 50 minutes and standard deviation of 10 minutes. That's a long way to write it, okay? Statisticians adopted a shorthand notations for that. Here is how to write it in a short way. Time to assemble a computer, I'm going to use capital T, okay? Right here, capital T, to denote the random. It's a random variable, right? From computer to computer, it's a different number. It's a random variable. So time to assemble a computer, random variable, is distributed. Distributed is a tilde sign. Distributed normally is capital N. And then in parentheses after the letter N, I'm going to specify 2 things because that's what it takes to specify fully the normal distribution, right? First of them is mean. I can write mu equals to 50. And second, the standard deviation, sigma equals to 10. Okay? So this is a short way to write the same exact thing. Time to assemble a computer is normally distributed with the average of 50 minutes and standard deviation of 10. Okay? All right, and let's say that operations manager wants to find out what is the probability that a computer, randomly selected computer, takes anywhere between 45 to 60 minutes to assemble. Okay. Now let's actually, first of all, let's see if I can switch to the node. One node. No. Okay. Hold on. Let me make an adjustment again. Alright, so that I can show you the screen with ability to write on it. Okay. Changes. And okay. Alright. So here is what is going to look like graphically. Right? Question that we're trying to address. So this is my distribution. That's my horizontal line. And my distribution is normal, which means that it's bell-shaped. Looks like that. Okay. Alright. So the mean is 50. So that's the position of my peak. Mu is equal to 50. And the standard deviation, sigma, is 10. So standard deviation, I don't have a nice way to show on the picture. It's just the measure of how wide is the distribution, right? So my question is, what's the likelihood that a single randomly selected machine will take anywhere between 45 to 60 minutes to assemble, right? So let's say 45 is right here somewhere. That's my 45. Okay? And 60 is somewhere over here. That is my 60. Okay? So the probability graphically is going to be an area under this curve within the boundaries, right? So all this shaded area is my probability that time to assemble a computer is between 45 and 60 minutes. Okay? And I'll show that with an arrow right there. Okay? That's what I'm looking for graphically speaking. Okay? Now, unfortunately, the only way how we can find these probabilities is with the use of computers. Okay? Before we had computers probably 15, 20 years ago when computers were let's say in their infancy, right? Then to find these probabilities we used actually tables. So the normal distribution was tabulated, F distribution was tabulated, etc., etc. These days, when we have a software like Excel or JUMP, we can do the same thing much quicker using the computers. But we cannot, remember the previous example that we did with calculating probability that a student will answer precisely 2 questions correctly on a quiz by guessing, right? There is a formula underlying this probability, right? And we use the formula. It was very easy for us to unwind it, elementary computations, and here is the result. Unfortunately, it's not that simple with continuous distributions, okay? Not with all of them, but with normal is especially the case, right? To find the area under the curve, we have to use computing device. There is no way for us to do that with pencil and paper. So let's go back to JUMP, right? So here's JUMP, and let's use the same exact tool. That would be distribution calculator, right? So go to help, sample data. Okay, and teaching scripts, interactive teaching modules. Probably we should make a comment to them. They shouldn't hide this thing so far in help, right? In the next release of JUMP, they should make it one of the menus, right? So that you can quickly access that. All right. So distribution calculator, right there. Okay. And by default, I have normal already, right? The only thing is I need to modify my mean and the standard deviation because it's showing 0 or 1 right now. So my mean is 50, my standard deviation is 10, right? And it will adjust, it will adjust the display for me so that peak is at 50. Okay, and I'm looking for the probability within boundaries, right? So my lower, well, let's do the upper boundary first because it will curse at us. Because when your lower boundary is higher than upper boundary, that's just wrong. Okay, so my upper boundary is 60, my lower boundary is 45, right? 44? Ah, yeah, that's actually a good question. Should I go from 44 or should I go from 45? No. Or does it even matter? what's the probability that time to assemble a computer will be precisely equal to 45? 0, right? So therefore, if I go from 45 exactly, or 45 greater than excluding 45, doesn't really make a difference, right? Make sense? Because the only thing that standing between, so here, between 45 and 6, right? 60 is included and 45 is excluded, right? But what if I include 45? Will it make a difference? No, because it's only one number, right? And the probability of that number is 0, right? So I'm going to use 45 as my lower boundary and 60 as my upper boundary, okay? And here is the answer for you, 53.28%, okay? Now, actually it has a practical meaning. What kind of practical meaning? As the probability, it's not a very interesting question, right? I mean, who asks that question in the production settings, right? Can I come to the operations manager and ask him, hey man, what's the likelihood that a randomly selected computer is getting assembled between 45 to 60 minutes? There is another interpretation of the same thing. Because any computer with the likelihood of 53.28% is assembled between 45 to 60%, that actually represents the proportion of my production, all computers that I manufacture, right? That are assembled between 45 to 60 minutes. So I can say that if daily I'm manufacturing, assembling 5,000 computers, 53.28% of them take anywhere between 45 to 60 minutes to assemble. And that is a much more practical question to ask, right? Make sense? Oh, by the way, let's actually go ahead and do this one, right? So what is the likelihood that computer takes exactly 60 minutes to assemble? The answer we know right off the bat, right? The answer is 0. But how do we make the software to show that? Well, my lower boundary, upper boundary should be 60, and my lower boundary should be also 60, right? So if I go 60 and 60, then first of all, the area disappears, you can see, right? What's the area of the line? Nothing. Line doesn't have an area, right? And the answer at the bottom, well, because it's a software, right? It still applies certain algorithm and it calculates a number for you, and right there it says, well, the area is vanishingly small, less than 0.0001, okay? Which is for practical considerations, it's 0, okay? But that's basically to emphasize the point that I was trying to make at the beginning. Make sense? That should be simple enough, right? Okay, so let's switch back to PowerPoint. There you go. Okay. And the next couple of slides, I believe, they go through the same process as we did, right? Finding the probabilities using jump. So you go to teaching scripts, distribution calculator, you set up your mean and standard deviation, etc., etc. Okay? So this is what we did pretty much a minute ago. Okay? Here is another question. Let's see if I can actually switch back to jump. The company claims that most of its computers are built under 1 hour. What proportion of computers built do not satisfy this claim? What does that mean? That means that I'm looking for the probability, the time to assemble a computer. Under 60 minutes, yeah. What's the proportion of computers that do not satisfy? So they're built over 60 minutes, right? And the majority are under 60 minutes, under 1 hour, but there is a small fraction that take longer, right? Probably computers with the most features, right? And most installations and most testing, okay? So what proportion of computers take longer than 1 hour to assemble? Okay, so P, probability, the time exceeds 60 minutes, right? So let's see if I can make jump to show up. Doesn't show up on this screen, right? So hold on, I'm going to make the switch again. Screen resolution. All right. Changes. All right, so here's jump. And nothing changes in terms of settings, right? Oh, come on. Yeah, hold right there. Okay, nothing changes in terms of my mean and standard deviation. And now what I'm looking for is probability that x is greater than 60, right? So it gives me the probability in the right tail of the distribution. All these computers take longer than 60 minutes. And how many of them do we have? Approximately 15% of the computer, 16%, right? 15.87% of all computers takes especially long time to put together, right? Longer than 60 minutes. 15.87% of them. Okay, so it's very easy to find probabilities using software like Jump. All right, now let's discuss something else. Okay, we can ask kind of a reversed question, right? So far we were dealing with finding probabilities given the value, right? What is the probability between 45 and 60? What's the probability greater than 60? What's the probability less than half an hour? Probably not a lot of computers satisfy that, right? Very, very short time. But we can ask reverse question. If you know the probability, what is the value on the horizontal line? What's the value of the variable that gives you this probability? Okay, so here is the standard notations that again statisticians are using. Okay, so let's say I have a distribution which looks normal, right? Typical approach for the statisticians is to say, let's talk about right tail distribution, right tail of the distribution only. Okay, so here I have area, certain area, and total area is 1, so therefore it should be fraction of 1, right? Certain area in the right tail. Okay, let's say this is area A, whatever it may be, 0.2, 0.3, 0.05, whatever it might be. So the value of the random variable x that cuts off the area A in the right tail, I'm going to call x with the subscript A. Okay, so if the area is 0.3, I'm going to call it x 0.3. Right? If the area is 0.05, 5%, I'm going to call it x with the subscript 0.05, etc. Okay. So if area A is in the right tail and in the left tail, whatever is missing, right? Total area is 1, so 1 minus A, right? Okay, so here is another question, right? Reverse problem. Finding values when you know the probability. Computers with extra features take especially long time to build. We know that approximately 16% of all computers, from just what we did, right, just a minute ago, approximately 16% of the computers take 60 minutes or longer to assemble, right? But even among those computers, let's take a look at really high-end stuff, okay? Servers, complicated servers, for example, or hardcore gaming machines, you know, people who like, you know, play shooters, right, on high-definition screens. That require especially, you know, strong and powerful software, right? That requires fine-tuning. So these really powerful machines, they take a special long time to put together. So let's take a look at 5% of the most complicated installations, right? We want to know what time does it take to assemble 5% of the machines that require most of the work, okay? So in other words, graphically speaking, here's what happens, right? I have my distribution right here, okay? This is 0, this is 50, and the peak is at 50, right? Okay. So 5% of the machines with the most features, and therefore with the highest time to assemble, are going to be in the right tail of my distribution, correct? So it's going to be somewhere here. And 5% means that in the right tail, I should have an area of 0.05, right? 5% of the most involved machines, right here in the right tail, and the area in the tail should be 0.05, right? So therefore, according to what we just discussed, the notation, I'm going to call it t with the subscript 0.05, right? The value of the random variable time t that cuts me off 5% of the area in the right tail of the distribution. Make sense? Okay, so this is kind of a reversed problem, right? Before that, we knew the values, give me the probability. Now I know the probability, give me the value. All right? And by the way, just a comment, you realize that what I'm looking for is the 95th percentile of the distribution, right? Because 95% of the area will be to the left, lower than that, and 5% of the area will be to the right. So essentially, when I'm asking for the values, really, I'm talking about percentiles, right? Finding percentiles. Okay, cool. Darn it, I have to do it again. Every time when I switch over, it just changes on me. I don't know why.
You can't do like Alt-Tab?
Hmm?
You want an Alt-Tab?
Alt-Tab? No, I have to reset this thing. Okay, hold on. Duplicate this place, yeah. So that I show on my screen the same thing, and it shows on the projector for the entire class. It just keeps switching on me. I don't know why. It's probably part of what software does, the Camtasia Studio. All right. So I'm going to go back to my, yep, right there, to my distribution calculator. So type of calculation, that's the part that I need to adjust now, okay? Distribution parameters don't change, it's the same thing I'm working with, right? But notice that so far I was working with input values and calculate probability, right? Now I have to input probability to calculate the value, right? So switch right there, okay? And note that your calculation part also changes, right? Now what it's asking for you, first of all, what are you looking for? Are you looking for the left tail area or right tail area? Or enter the area and split it evenly between right and left tail, or central probability, same thing, right? Enter the area and it will compute the middle part. So I'm looking at the right tail of the distribution, correct? Right tail probability, and my probability in the right tail should be 0.05, 5%. All right, there it is, okay? So here's my area graphically. And here's my area numerically. So it says that the 5% of the most involved machines with most complicated hardware and software installation, right? It requires 66.44 minutes, right? So if you round that down, you get 66, right? So the most involved machines require not exactly 66 minutes, but 66 or longer, right? Because the area to the right from this value corresponds to longer times, right? In the right area, the right tail of the distribution. Make sense? Any questions? Easy, right? Easy breezy, beautiful Powerpuff Girls, right? That's what I always say, and a lot of students like that. Also, I say at the end of the class, typically, okay, we're done for today, so now go to Chick-fil-A and have, sandwich or salad. And one student in the last semester, they liked it so much, like, he's graduating, so he said, say me go to Chick-fil-A one more time, please. So, I'm not affiliated with Chick-fil-A, okay, legal disclaimer, so I don't benefit from putting a word out there for them. All right, anyhow, let's go back to our slides, right? Couple of examples that I wanted to do. So example number one, you know what, maybe the reason why it keeps switching on me is because when I go full screen it changes the settings. So how about I just keep the slides like that and don't go to the full screen. Maybe it'll change something. Alright, so let's do the example. I like this one actually, about McDonald's. Okay, how much money does a typical family of 4 spend in McDonald's? McDonald's, is primarily kids, well, not primarily, but big part of their marketing is they are appealing to children, right? They have all this play area, playground, etc. They have kids meal. Adults go there too, right? For just to get the meal, not to play on the slide or anything like that. So family of 4, well, you can expect at least a couple of Happy Meals probably, right? Big Mac for mom and dad, and probably big drinks, right? So interesting question to ponder for McDonald's would be, how much money can we expect from when family of 4 comes to McDonald's, right? So let's say that they collected a whole bunch of data and they estimated that the average amount that family of 4 spends is, where is it? Yeah, right here, right? $16.40. But of course, not every family spends exactly that amount, so there is variability, right, from family to family. So there is a distribution. So how do you characterize the fact that you have distribution? Not all numbers are the same. You give a standard deviation, right? How wide is the distribution? $2.75. And they determined that it's approximately normally distributed. Like I said, nothing is ever exactly normally distributed, right? It's a good approximation. So what we're getting is mathematically accurate result, but that does not necessarily 100% accurately reflects the reality, because after all, it's just a model of what's going on, right? Okay, so find the probability that a randomly selected family spends less than $10. Okay, probability that they spend between 15 and 20 bucks. Then below what amount? 10%. Only 10% of the families spend at McDonald's, and also where is your 50% of spenders, most typical population, right? So let's start with these two questions first. Less than $10 and between 15 and 20. Well, from the general standpoint, by the way, what do we expect? Less than $10. That is going to be a high number or a small number? What do you think? Small number, right? Why? Yeah, $16.40. But also another important part is standard deviation, right? Yeah, way off, exactly. So if if you get two standard deviations, how much you get? 275 times 2 gives you 550, right? Is that 550? So from 1640, you go down 550, you're still approximately sitting at $11, right? So it's more than 2 standard deviations away, right? And remember, we discussed yesterday that if you have a bell-shaped distribution, 2 standard deviations away, you get 68% of the day, right? 1 standard deviation, I'm sorry. 2 standard deviations, you get 95%, right? And only 5% in the tails, right? Combined tails. 99% if you have 3 standard deviations away, right? So that part is between 2 and 3 standard deviations away, right? $10 is more than 2 but less than 3 standard deviations away, right? So we should get actually very small percentage, right? So to anticipate the answer kind of thing, right? Okay, so let's switch to the distribution calculator, and I have to adjust my mean now, right? 1640 is the average, and my standard deviation is 275, right? And I'm computing probabilities now, right? Given values, compute the probabilities, okay? And I have to look at less than a number, right? And that number would be 10, okay? 10, and there you go. Graphically, it looks like a very small area, right? Very teeny tiny tail. And the tail actually, numerically, represents what percentage? Only 1%, right? So our kind of intuition that we were discussing was right. Not a lot of people falling into this category, right? Spending $10 or less, okay? So now let's take a look at between the values, okay? So we have to go from $15, I believe, to $20, right? To $20. And that would be the area in the middle, obviously, right? Somewhat in the middle. So that actually represents a significant chunk of all customers, families of 4, right, that go to McDonald's. So what does that tell you? About 60%, right? 59.94. So a good portion of their customers, 60% of everybody, goes to McDonald's, leave behind with a couple of kids, right? Family of 4, leave behind anywhere between $15 to $20. So it's easy to compute these probabilities. Now let's take a look at the reverse problem, right? 2 other questions actually ask the reverse problem. Knowing the probability, find the value. So one of them tells you, well, what about 10% of the most economic families, right? That do not spend a lot of money in McDonald's, and we have 10% of these people, right? Below what amount only 10% of the families of 4 spend in McDonald's? Again, graphically, I can have normal distribution, right? Like this, with the peak. Peak happens at the mean, which is 1640, right? And the standard deviation sigma is 2.75. And my most economic families, they are located in right tail or left tail? Left tail, right? Left tail of the distribution, and 10% corresponds to the area in the left tail, therefore, right? So this shaded area right here is 0.1. And I'm looking, therefore, for t with what subscript, by the way? 0.9, right? Because remember, subscript tells you the area in the right tail. So if in the left tail I have 0.1, in the right tail I'll have 0.9, right? So I'm looking for 0.9, t.9, right? And that represents, by the way, 10th percentile of my distribution while we're on the subject matter, right? Because 10% below that and 90% above that, right? So really I'm looking for the 10th percentile. Okay. So I have to switch here, type of calculation. It's not probability given value, it's the value given probabilities, right? And I'm looking now in the left tail of the distribution, and the probability in the left tail is going to be 0.1, all right? And what does it tell me? It tells me that 10% of the most economic families spend $12.88 or less, right? Make sense? And the last question, I believe, was about what is your most typical customer spending, right? So 50% of families in the middle. So what, to rephrase that in terms of the percentiles or quartiles, what am I looking for? Interquartile range, exactly right. I'm looking for Q1, that's first quartile, and Q3, right? Because in between Q1 and Q3, I have 50% of data in the middle. That's precisely what I'm looking for. Now, here I'm going to actually do this. I'm looking for central probability, right? And central probability corresponding to half of the area, that would be 0.5, right? So therefore, my first quartile is $14.55. And my third quartile, right there, is $18.25. Okay.
You can also do a detailed model for it.
Oh, absolutely. Yeah, I can. It's going to be the same thing, but colored differently, right? That's it, pretty much. But the same values. Nothing will change. Make sense? All right. Now let me show you. We still have 15 more minutes, right? So let me go ahead and show you a special standard distribution. Special normal distribution, okay? And this is the part where I always talk about ancient statisticians, okay? So statisticians who existed even before the invention of computers, right? Who were basically paper and pencil-based statisticians. By the way, a little bit of history. Normal distribution is also called Gaussian distribution, oftentimes. And it's named after the German mathematician who made actually a fairly large contribution to mathematics, Karl Gauss. Okay, so he proposed normal distribution first, and therefore normal distribution oftentimes is also called Gaussian distribution. Okay, Karl Gauss lived in, I believe, 18th century. So we, as a humanity, we're familiar with normal distribution for approximately 300 years by now. Okay. Now, 300 years ago, they didn't have computers, right? They barely had paper, okay? So, let me ask you this question. In order to fully specify the normal distribution, I need two parameters, right? We discussed that. Mean and the standard deviation. Are there any limitations on how large or small the mean can be? No. Can the mean be negative? Let me ask you differently. It can, right? Can you give me an example of something that is distributed with negative average? Below zero temperature, right? You go to Antarctica, right? I doubt that they ever have positive temperatures out there, right? Below zero temperature, right? Less than zero mean. How about standard deviation? We actually discussed that yesterday. Are there any limitations on standard deviation? In other words, let me give you a hint. What's the smallest that the standard deviation can be? Zero, right? Zero is the smallest thing. If all of my numbers are identical and absolutely the same, then I have no variability, zero standard deviation, right? But it cannot be negative, right? So therefore, if you kind of think about normal distribution, let me kind of scroll to the very beginning of this slide deck. Okay, here, right? Normal distribution takes two parameters, mean and the standard deviation. There is no limitation on what the mean can be. Positive, negative, large, small, zero, anything, right? Sigma can be zero or more. Well, you never see zero in practical, right? In practice, you never. Okay, that's bad. As a matter of practice, you never have zero, right? But sigma can be anything positive. It can be 1, it can be 10, it can be 0.3, etc. Okay? So, coming back to the prehistoric times when we didn't have computers, right? If there is infinitely many choices of the mean, and essentially infinitely many choices of sigmas, right? How can we tabulate every single choice of sigma and every single choice of the mean? I mean, every time when you change something, like let's say, for example, in previously considered case with Dell computers, right? The average is 50 and standard deviation is 10. We have a table that basically tells you what are the areas under the curve for that specific combination. But you change one thing, instead of 10, your standard deviation becomes 15, everything changes, right? You need another table. So how do we do that? Well, statisticians, or mathematicians in general, figured out that every normal distribution can actually be reduced or modified to form a special normal distribution. And that's called standard normal distribution. Okay? So standard normal distribution, statisticians just basically said, let's pick a certain number for the mean and certain number for the standard deviation. Some numbers that we're comfortable about, psychologically satisfying numbers. So they said, mean equals to 0 sounds like a good deal. Let's set mean equal to 0. And standard deviation of 1, let's do that, okay? So sigma 1 and mu 0, that combination gives you standard normal distribution. And my claim here is that any normal distribution can be reduced to the standard normal, okay? That is the process called standardization. So here is the formula basically, okay? If you have x, some variable x, whatever it might be, it can be time to assemble computer, or heights of people in the humanity, in the society, you know, or amount of money. Well, that's a bad example. We know that the amount of money is skewed distribution, right? It's not symmetrical. But height probably is a good example, right? Some people are very tall, some people are relatively short, but most people are kind of in the middle range, right? Okay, so if you take something that is normally distributed, subtract the mean that you know, and divide by the standard deviation that you know, you get another variable out of that, right? And that variable is going to be distributed. If x is normally distributed, then this z that you get out of that is going to be distributed with the standard normal distribution. It's actually pretty easy to see. Why? Because let's say your mean is positive, so it's somewhere over here, okay? When you subtract the mean, essentially what you're doing is you're moving all the points to the left by the distance of mu, right? So the new peak of your distribution is going to be at 0, right? But the width is still going to be whatever sigma you had, right? So if sigma is less than 1, the distribution is going to be very wide, right? If, other way around. If sigma is greater than 1, high, right? If sigma is high, distribution is going to be very wide, okay? If sigma is small, distribution is going to be very sharp. So when you divide by sigma, essentially what you're doing is you're changing the shape of the distribution, okay? And therefore, you pretty much adjust the shape of the distribution so that it looks like this, standard deviation of 1 and sigma, and the mean equal to 0. So this process is called standardization, okay? So the standardization later can be used in order to find the probabilities, okay? So therefore, the only thing that we need really to find any probability for any normally distributed variable is to know how standard normal is distributed. And here is a good example, okay? So I'm going to write it on the board, actually, what you see on the slide. So suppose, or I can switch, you know what, let me switch to the note taking the application right there, okay? So that we'll all see that and it all becomes part of this video, right? Okay, so again, z, right? In order to standardize, all I have to do is take x, subtract the mean mu, and divide by the sigma, right? So remember the first question that we had during this lecture. What is the probability that, let's say x is the time to assemble computer, which is distributed normally with the mean of 50 and the standard deviation of 10, right? And we were looking at the very beginning, what's the likelihood that a randomly selected computer gets assembled between 45 to 60 minutes of time, right? Remember the probability that we found? It was actually 0.58 something. No, it should be higher than that. Yeah, I don't remember, quite honestly. Well, we'll figure it out in just one sec. Okay, so here is basically what I can do. All right, I can write it out a little bit differently. So I'm going to write it again, but now I'm going to have more space to do my manipulations. Okay, so I'm looking for probability that x is between 45 and right here 60 minutes, right? So what I'm going to do is perform manipulations with this expression in parentheses in order to get a z in the middle, okay? So you can see that the first thing that I have to do is subtract the mean, right? So let's do this. If I subtract the same number from all parts of inequality, I'll get the same inequality, true? If I subtract number 3 from all parts of inequality, it still holds, right? So I'm going to subtract the mean from the x, and of course I'm going to subtract mean from the left side and from the right side. But now I'm going to get numerical, okay? Mean is 50, so I'm subtracting 50, and I'm subtracting 50 from another side, okay? All right. Now I have to get a z, I have to divide all parts by sigma, right? And what's good about this is sigma is never negative, right? Because if that was negative, dividing by a negative number flips the signs, right? Just like multiplying by a negative number. If I divide by a positive number, signs stay the same. That's what's good about that. So if I divide both parts by sigma, all parts actually, not both, all 3 parts by sigma, sigma is positive, I can keep the signs. And now again, I'm getting numerical. Sigma is 10, so this is specifically 10, and this is specifically 10. So in the middle, you can see that I'm getting a z, right? Standard normal. And I'm going to write it out. Z is distributed normally with the mean of how much? Standard normal mean is equal to 0. Yep. And the standard deviation of 1. All right. So my original question, what's the probability that the computer gets assembled between 45 to 60, is the same thing as to ask, what is the probability that a standard normal variable is between something and something else? Okay, what's the first something? 45 minus 50 gives me minus 5, and divide by 10, minus 5 by 10, negative 0.5, right? And the other one, 60 minus 50 is 10, divided by 10, positive 1. So you see that? My original question about time, which is normally distributed with a mean of 50 and blah, 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 is actually the same thing as this weird z variable, which is standard normal between minus 0.5 and 1. Okay? And let's go back to, what's it called? Jump, right? Let's go back to jump in order to find out that this is exactly the same thing. So I'm going to go to jump. Thank God it didn't switch the screen on me. All right. So now I am adjusting my probabilities, right? Oh, not probabilities, the mean and standard deviation, right? So 50 is my mean and 10 is my sigma, correct? To make the distribution look right. And I'm looking to find probabilities, right? Not the values given the probability. Yep. So my original question was between 45 and 50, right? 45 and 60. So my upper limit is 60. Remember, you have to adjust the upper limit first. And the lower limit is 45. Bam. So my probability that I am assembling a computer anywhere between 45 to 60 minutes is 0.5328. I'm going to write that down. 0.5328. Okay? Let's show. So, by these arguments that we just made numerically, I should get exactly the same result if I'm switching the gears and talking about normal distribution, right? It should give me exactly the same numerical answer. Well, let's see if that's true, if I was lying to you. All right, so I have to adjust my mean and the standard deviation. So for the mean, I put 0, and for the standard deviation, I put 1. And I'm adjusting my limits, right? Lower boundary gets minus 0.5, and the upper boundary gets plus 1. Is that the same answer or what? It is the same answer, right? So this, ladies and gentlemen, is how ancient statisticians in the pre-computer era were thinking about normal distributions, okay? You do not have to tabulate every single possible combination of your mean and standard deviation, because infinity is the name of this exercise, right? Really, you don't need to do that. If you use just this simple, oops, where is it? If you really use just this simple trick right there, okay, normalize, or not normalize, standardize your normal distribution, all you have to do is tabulate just one normal distribution, standard normal, right? And every single problem about any possible mean and any possible sigma essentially is converted into the problem about the standard normal distribution, okay? So this is how things were performed in the pre-computer era, all right? Make sense? Any questions, concerns, complaints, sarcastic comments? All right, and this is it for today. Okay, and the homework number 3, right, is posted out there. The homework is about distributions. Okay, it's about binomial that we discussed today and normal that we just discussed also. And remember, I told you that if you know the distribution, you do not need the data set because you know pretty much everything that's out there to know about that, right? So the problem, 2 problems on the homework, they do not require a data set. The only thing that you need is use jump, specify the right distribution with the right parameters and answer the questions, okay? All right. Oh, one more thing. Tomorrow we have an exam, right? And I posted the study guide, correct? And you received the email with the study guide, right? So the exam is going to contain 2 problems, and I believe it's 10 multiple choice questions, right? So it shouldn't be too hard. Probably it's going to take us about an hour to go through the exam, right? And after the exam, we're going to start a new topic, and I'll grade the exams and bring them next day, and we'll go over them in class, okay? All right. Thank you so very much.